So now we are going to the Rutherford model. Rutherford says, oh, there is a nucleus there, and then there are negative charge particles going around in the shell, right? So what is a nucleus made up of? Today we are studying atoms as a whole, but what is nucleus made up of? What is nucleus? Good, yeah. I think everybody has understood very well in chemistry classes. I'm getting 100% right results so far, but only 56% students have responded. Why? You got to respond more. Now come the wrong answers. I'm not sure if you are doing that on purpose, but that's not explainable because this is something you have studied in science classes at junior level also, right? Protons and neutrons. Electrons are the one that are around, right? So protons, neutrons live inside of it, and then electrons go around it. Okay, everybody clear with that? Yeah. Now there was a few problems with this model. First of all, now I don't know if you remember this, you should remember. I told you three stages of a charge. Charge is stationary. What is around this charge? It is stationary. Velocity zero, acceleration zero. What kind of field does it have if there is a stationary charge? Tell me in the chat box. Yes, Arvind Thakur, it's electric field. Now the electron or any charge, doesn't matter, electron, proton, alpha, whatever, has a velocity and has no acceleration. What does it have around it? Yes, Manjushri says it will have magnetic field in addition to electric field. Arvind Thakur also says that, right? Now let's say there is an electron and that has a velocity, let's say 1000 meter per second, but now it also has acceleration, 200 meters per second square. What should this do? Yeah, Tripatil, you were right. Yeah. Now, Tripatil and everybody tell me what should this do? There is an accelerated charge. It's not moving just, it is also accelerating. The speed is increasing or reducing, whatever, or the velocity is changing. Yeah, Rukaya says it should have electric field fine, magnetic field fine, but it should emit photons, electromagnetic radiations. It should give out photons. But if it gives out photons, isn't it losing energy? Like, right? If photons are energy, energy cannot be created nor destroyed. So if electrons are emitting photons, they got to lose energy, right? Now, if you look at this model here, are the electrons not accelerating? Yes, they are accelerating. There is a centripetal acceleration. Yes, Atri, you're right. When you lose energy, basically behind the scenes, you lose mass, right? So now what we are saying is if electron is emitting, electron is going in a circular path. Circular path means it is acceleration, even though the speed can be same, but your direction of velocity is changing. So it is an accelerated motion. So now if you're telling me that this is going in a circle, then it got to emit out radiations, it got to reduce the speed, but if it reduces the speed, it should spiral right into because it's losing energy. And within a flip second, not even a flip second, microsecond or picosecond, the atom should die. But the atom is not dying, right? So now let's see the limitations formally here. What was wrong? So first of all, these were the conclusions made by Rutherford. Most of the alpha particles pass through it deflected. That means atom is empty. As I was saying, if this room is atom, this is the nucleus. So everything will be just going here and there. Nothing is going to hit this tiny tip of the pen, right? Some alpha particles are deflected by small angle. So that means that they go close to the nucleus. So alpha particle was going here, it'll be deflected little because this is positively charged, and that is why alpha particle is deflected. Occasionally, an alpha particle travels back. That means nucleus carry almost every mass, like everything, the mass itself is inside the nucleus. Electrons do not have mass, almost virtually almost zero, I would say, compared to nucleus, obviously, right? So most of the mass is out there in the nucleus. Now, an atom has a small, dense, positively charged nucleus. We covered that electrons move around the nucleus in circular orbits. Electrostatic force between opposite charges required. So this is more like, and this is also wrong, basically. I mean, all these models are eventually wrong. So this is a positively charged thing. So electron has a centripetal force, the Coulomb's force, right? K times the number of protons in there times this divided by the radius square. This is the centripetal force. Okay, so Ninad has asked a very good question. How do you analyze the degree of deflection? You use Mr. Newton here, right? So once it is deflected, Newton says it keeps moving. So you have a sensor here, and you know what percentage of the total alpha particles were hitting here. Then you put your sensor here, you know what percentage was hitting here. You put a sensor here, what percentage was hitting here. Once deflected, there is no force after that. It keeps going in a straight line. So you get that angle. Okay, so this part is clear. Electrons are going around this because of the centripetal force provided by what part of is not clear, Ninad? Like centripetal force part? Like kind of like say sun and earth, right? Which is wrong comparison actually. This is completely wrong. So this is a centripetal force provided by gravitation. And this is what is being said in the classical. This is again part of like classical as of now, that not classical but wrong thingy, that electrons are attracted there and it's more like a particle. But for now we'll say like gravitational force here, Coulomb's force here. So which part, Ninad, I'm not understanding. So you have sensors here. No, you cannot see alpha particles. You have a sensor here that senses an alpha particle. So let's say you put in a 1 million alpha particles go through this, and you see maybe 1000 here, you know how many are going through this angle, isn't it? Do you get it? Okay. So now total energy is potential plus kinetic energy. No, because what is potential energy here? Potential is because of remember the Coulomb's energy. So two charges Q1 and Q2 at a distance of d have a potential energy of k q1 q2 by the distance, right? The distance is d. So when you have an atom here and then you have electron here, electron has some potential energy because it is bound by this proton. The structure of proton there, it has some potential energy, but it also has some kinetic energy because it is moving now. Does everybody understand this part? Kinetic plus potential, that is the total energy of the electron out there. Right, so that is being said here, total energy. Now, can anybody tell me, okay, let me write a question and then ask you. So total energy will always be negative. So give me the answer. Is this true statement or is it false statement? So the statement here is the total energy of the electron will always be negative. That's a statement I'm making. Is it true or is it false? So 30% students have responded. Ninad, your answer is right. Arvind, your answer is right. I don't know who else answered. Atri, yeah, you're right. Yeah. Good job there. Like most of the answers in the poll also are right. Yes, good, awesome. Right. So whoever does not understand, let me explain this. Oh, by the way, true is the right answer. 80% students said. Now, uh, potential energy, right? Potential energy is going to be negative because it's an attractive force here. And that is going to be more. It's actually, as we'll see in the coming up slides, it's going to be double in magnitude to the kinetic energy. Okay, and this is something you studied in your gravitation chapter also, by the way. So potential energy will be 2 times of kinetic energy, but negative of it. We will see in the coming up slides here. Okay, so the total energy will be equal to kinetic energy minus 2 times of kinetic energy. So total energy will be equal to minus of kinetic energy. Anyway, so if kinetic energy is is 5 joules, total energy is negative 5 joules. Potential energy is minus 10 joules. That is always going to be the relationship when you see in gravitation and also here. Okay. Can I move on? Is this completely clear so far? Say yes or no. Is this completely clear? Monisha says okay. Arvind says Linus is clear. Okay. Okay, whatever is not clear, you have to tell me. Shivangi is saying fine. Okay. So two major drawbacks. One drawback we already covered. It has to be emitting some kind of photons here, and then if it emits photon, it loses energy. If it loses energy, it comes closer because farther it is, more energy it had. So if it is having less energy, it got to come closer. Its potential energy has to keep reducing, right? Negative or whatever way you look at it. So total energy is less when you're closer to the nucleus. So it should spiral in and instantaneously, almost instantaneously die. Now another problem is if it is doing that, then it is emitting. See, we'll see the calculations. There is certain frequency, so certain energy it has here. That energy is equal to h times nu, right? Does everybody understand this? Energy of a photon is the Planck's constant multiplied by the frequency, right? So now there was some energy, then there should be less energy, less energy, less energy. So the photons emitted should be in a continuous spectrum. But what you notice instead is if you look at hydrogen, you have certain lines in there. So there is nothing except these lines, as if this was quantized. Same thing with neon and iron. I mean, whenever you see these spectral lines, they're quantized. Does everybody understand quantization? We covered the quantization when we started electrostatics. Do you understand quantization versus continuous? Everything in the world is quantized. Energy is quantized, mass is quantized, everything is quantized, right? So now here you're seeing it is all quantized. Right, so that is another drawback. It's a line spectra instead of continuous spectra. You should actually see this spectrum, not these lines. What are these lines doing there? Right? Now comes the Bohr's model. Right? Bohr is giving us two postulates. So postulates are basically statements. So statements that you make without giving any proof. These are the statements I'm making, and then everything else in the theory is based of these two postulates, right? That these are postulates. If you ask me to prove this, I cannot. You have to take them as true for granted, and then you move on to read the thing. When you do relativity theory of special theory of relativity, Einstein is giving us two postulates. Now, if you believe in these two postulates without asking any proof, you can study the relativity. Everything makes so sense. Everything is so easily understood. As soon as you question one of these postulates, nothing makes sense to you now. And this is how postulates work. So now Bohr is giving us two postulates, and let's see on the next slide what these are. And based on these postulates, he is proposing a little better version of what Rutherford has given us. Now, let's see first the postulates, following postulates, right? So number one, electron in an atom can move around the nucleus in certain circular stable orbits without emitting radiations, right? So what he's saying is the atom is structured such that electron can either be here, or it can be here, or it can be here. You cannot have the electron here. It's impossible. So these are quantized now. It can either be at level 1, level 2, or level 3. It's like you can be on step 1, step 2, or step 3. You cannot be at step 1.1. So these are now quantized, right? Now, when they are moving in these levels, these are stable levels, right? So these are stable. When you go in them, there is no energy emitted. There is no photon emitted. Even though you're accelerated, the electron does not emit any. Now, nobody was able to prove this until Heisenberg's uncertainty principle came in. When you study that, which is not in your curriculum, when you study that, you will start visualizing these as waves. And these are standing waves that you have studied in your 11th grade course. So these are stable waves, right? These are standing waves. These are stable. So when you have stable waves, you don't have any energy transmitted, and that is the reason why these are not there. But we are not talking of that. When Bohr gave this explanation, he is just blindly saying that statement. Anybody who does not understand these two statements, please ask me. There is a very less response from the class today. So when I'm saying yes or no, you're responding, but nobody is writing anything except few students like Ninad and Arvind Thakur, Shivangi, Rhythm. Few students have written for sure, yeah. Sai Kumar. Yeah, please, anybody who does not understand. Okay. 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 So these stationary orbits are the only orbits permitted, and there's nothing else permitted. But then when you are in an orbit that is called stationary, there is no energy being released. So now all those, see, now the thing is very, and then third thing is these are the postulates, right? Third is not a postulate, or maybe third postulate also, which was part of the previous one anyways. So when you're coming, so let's say there was electron where it was starting, it was here. Let's say it's here, it has more energy. Right. Now let's say it jumps here. When it jumps to the lower energy level, that energy cannot be destroyed, and that energy is actually released out as photons. Now, if the electron was here and it jumps here, it cannot create energy. It has to absorb a photon. So it absorbs a photon and then it goes to a higher level. And when it goes from higher to lower, it releases energy. And that explains those lines. Because I'm using very vague numbers here, very, very vague number, obviously, for now to get you started. Let's say this energy level was 5 joules. This was I'll just write the number 5 joules, 3 joules, and 2 joules. When it goes from here to here, the only energy you get is either 2 joules, or it can go from here to here and you get 3 joules, or it can go from here to here and you can get 1 joule. So there are only three energies possible, and for each of these energies you can say is equal to h nu, and you can find the frequency of that, and that frequency means the color. So in this case there are only three wavelengths possible, and that explains those lines instead of continuation, because electron cannot go from here to here and say, oh, let me, instead of emitting the full 2 joules, let me emit 1.39 joules. That is not permitted. Electron can never be there. ठीक है? Can we move on from here? Okay, so I'm assuming everybody is clear. Linus Joy has written earlier, he understood. Sorry.